Welcome students, welcome again to my new lecture. I am Muhammad Tanbir Ahmed, lecturer at Department of Civil Engineering, World University of Bangladesh. Measurement of yield of underground sources or aquifer. The yield of an aquifer or underground sources can be estimated by two practical tests in the field, which are pumping test and recuperating test. And these two tests can directly indicate the yield of an aquifer. First, we will introduce about pumping test. In this system, a well is constructed through the aquifer by which yield is to be estimated. Water is drawn from the well to cause a heavy drawdown in the water level. The rate of pumping is changed and so adjusted that it becomes constant. In this condition, the rate of pumping will be equal to the rate of yield, and hence from the rate of pumping, the rate of yield can be directly measured for a particular drawdown. However, it is impractical to adjust the rate of pumping and very difficult to keep the water level constant. Recuperating test. A well is constructed through the aquifer from where yield will be estimated. The water is first drained out to cause a sufficient drawdown. The pumping is then stopped. The water level in the well will start rising up, and the rise is noted at regular intervals of time till the initial level is reached. Knowing the area of the well and the rise of water level, the volume of water yielded in the given time interval can be worked out at different drawdowns. It is found that the yield is higher at higher drawdowns. These tests are generally conducted during the driest periods of years so as to know the yield under the worst conditions. We will use Thiem's formula for unconfined and confined aquifers to estimate the coefficient of permeability K and discharge capacity Q. This figure represents the unconfined aquifer based on Thiem's formula. And to estimate the coefficient of permeability and discharge capacity, the laboratory setup in the field will be like this. Here, this is the main pumped well from which water will be pumped out. And these two are the observation wells, well 1 and well 2. This D is the initial depth of aquifer. Here this is water table and this is the groundwater level. When water is pumped, this water table will lower and creates this drawdown curve. Here this HW is the static height of main pumped well, and SW is the depth of drawdown of the main well. When pumping continues, the drawdown curve will reach to this observation well 1 and observation well 2, and as like as main pumped, H1 is the static head or static depth of water in observation well 1, and S1 is the drawdown depth in observation well 1. Similarly, S2 is the static head for observation well 2, and S2 is the drawdown depth for observation well 2. R1 and R2 are the center to center distance from main well to observation well 1 and observation well 2 respectively. RW is the radius of main well. Again, from Darcy's law we know Q equal to KIA, where I equal to hydraulic gradient, K equal to permeability of soil, which is a constant. And from this Darcy's law, the Thiem's formula can be derived as follows: Q equal to pi K into H2 square minus H1 square divided by 2.3 log 10 into R2 by R1. And in this equation, the term H2 square minus H1 square can be simplified as H2 square minus H1 square equal to, we know, H2 plus H1 into H2 minus H1. And this H2 minus H1, that means the difference of static head can be written as the difference of drawdown, which is equivalent to S1 minus S2. And it can be written from the experimental setup of unconfined aquifer in observation well 1 and observation well 2. And if the amount of drawdown, that means this H2 and H1 is very small compared to the saturated thickness, that means compared to the initial thickness of aquifer D, then H2 and H1 are nearly equal and each of them can be written as same as the saturated thickness, that means D. So we can write H2 and H1 as D if the drawdown is very small. If the drawdown is very small, we can write static head H2 and H1 as D. Therefore, H1 plus H2 becomes D plus D equal to 2D. And the simplified equation becomes, this was the simplified equation, that was H2 square minus H1 square. And finally we got H2 plus H1 into H2 minus H1, which is equal to, this H2 minus H1 was equivalent to H1 minus H2, and this H2 plus H1 is equivalent to 2D. So we can write this is equivalent to H1 minus H2 into 2D. And if we replace this value in equation 6.6, we will get the equation Q equal to 2 pi k d into S1 minus S2 divided by 2.3 log 10 R2 by R1. Again, introducing coefficient of transmissibility T instead of K in equation 6.7, and finally we get Q equal to 2 pi T into S1 minus S2 divided by 2.3 log 10 into R2 minus R2 by R1. And these two equations 6.7 and 6.8 are called Thiem's formula for unconfined aquifer. We can use both these two formula. This figure represents Thiem's formula for confined aquifer, and the experimental setup is same as unconfined aquifer. Here, as like as unconfined aquifer, this is the main well, this is observation well 1, and this is observation well 2. This is the drawdown curve, and we know in confined aquifer there is a upper impervious layer above pervious stratum or pervious layer. So this is the upper impervious layer and this is the pervious layer or pervious stratum. This D is the total depth of the aquifer. This H represents the depth of pervious stratum or pervious layer. S1, H1, H2, S2, SW, HW, R1, R2 both are as same as unconfined aquifer. And again from Darcy's law we know discharge Q equal to KIA, where K is a constant, I equal to hydraulic gradient, and I can be written as dH divided by dr, and A is the area of the circle of influence, which can be written as 2 pi RH, that means the total area of the circle of influence. And finally we get Q equal to 2 pi k RH into dH by dr. If we replace the term dH by dr into left side, we will get this equation number 1. Finally, if we integrate the equation between the limit r1 and r2, we will get finally the equation of discharge Q equal to 2 pi k h into h2 minus h1 divided by log E into r2 by r1. And since we know log E equal to 2.3 log 10, we can also write Q equal to 2 pi k h into h2 minus h1 divided by 2.3 log 10 into r2 by r1. This is the discharge equation for confined aquifer based on Thiem's formula. Again we know the difference of static head H2 minus H1 is equal to the difference of depth of drawdown, which is S1 minus S2. So we can replace this H2 minus H1 by S1 minus S2, and the equation becomes, or equation looks like as 6.9. And again if we introduce the coefficient of transmissibility T, which is equal to Kd, and we can also write for confined aquifer T equal to Kh, and if we replace this T instead of Kh, the equation becomes as like as 6.10. So that is the end of our today's lecture. Thank you everyone.